Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. First off, thanks so much to everyone who sent in their favorite quote from last week's podcast. Your stickers are on the way. We had a bunch of fun with this contest and we've decided to continue it while our sticker supplies last. So definitely send us your favorite quote from today's show as well. You can do that via a comment or post on Facebook, Twitter, YouTube, or SoundCloud, as well as the show notes page for any episode of the show. Okay, and now about today's show. I've got a very special guest this week. His name is Evan Wright, and he's Principal Data Scientist at Anomaly. If that name sounds familiar, it's because Evan was the winner of our O'Reilly Strata+Hadoop World ticket giveaway earlier this month. Evan and I met up at the conference last week and got to chat about a number of topics in the realm of machine learning and cybersecurity. We discussed the 3 big problems in cybersecurity that ML can help with, the challenges of acquiring ground truth in cybersecurity and some ways to do it, and the use of decision trees, generative adversarial networks, and other algorithms in that field. I think you'll really enjoy this show. Speaking of cybersecurity, that's just one of the many topics that will be covered in the Future of Data Summit event that I'm hosting May 15th and 16th at the Interrupt Conference in Las Vegas. At the event, Diana Kelly, a global executive security advisor with IBM, will be talking about the future of securing cloud, IoT, and big data systems. We'll also be giving you a glimpse into the future of machine learning and AI, so-called fog or edge computing, augmented and virtual reality, blockchain, algorithmic IT operations, and much more. You can learn more about the summit at twimlai.com/futureofdata. And now, on to the show. All right. Hey, everyone. I am here with Evan Wright, Principal Data Scientist with Anomaly. You may remember Evan's name because we announced him as the winner of our O'Reilly Strata+Hadoop ticket giveaway. Evan and I decided to get together and record a little show. Evan, say hi.
Good morning, everybody. Good afternoon or good evening as it applies.
Awesome. So, Evan, why don't we start by having you talk a little bit about the company you're at and what you do there.
Sure. So at Anomaly, we are focused on threat intelligence. I think there's really 3 big problems in cybersecurity that are really ripe for using machine learning to improve. So one problem is malware detection. Another problem is threat intelligence, which is really the focus of our work. And another one is sort of stream detection of when you've got a series of events, like, for example, network traffic, trying to sift through that and find the security relevant concerns out of that stream. So we're focused on the latter 2 the most, especially as far as understanding threat intelligence better. So threat intelligence is this idea of, imagine you're conducting an investigation, like if you're a law enforcement, you would collect pieces of evidence and try and stitch together the story of what happened, and if possible, try and stop bad things happening before they actually occur. So something similar is the case in organizations. They run these security teams, and security teams want to know things like, of all the things that our network is talking out to on the internet, are some of those malicious? Right? And they want to be able to separate that. So threat intelligence fundamentally is understanding the tools and the infrastructure out on the internet and in your network to be able to separate those, right? So very pragmatically, it's something like a list of IPs or domains to start with, which if your network has activity going to these IPs or domains, then it would be malicious. So a lot of our main focus at Anomaly is we create a threat intelligence platform. The idea is there's all these security vendors out there which kind of give us this ground truth. And in security, ground truth is so important. It is really the fundamental problem and why machine learning is hard in cybersecurity, because ground truth is really expensive. We're not exactly spoiled in some sense like having image data, like having video data. Because in those spaces, you have a very clear sense of what data should I collect and what data do I care about. If you look at an image, it's easy to tell if it's a cat or not, to have that ground truth for labeling images. In cybersecurity, it's much harder. Instead of just being a layman who can look at an image and tell you it's a cat, in the case of cybersecurity, usually you need a very specialized expert to be able to tell you if you want really good confidence. They often need to be even more specialized because the best ground truth comes from analyzing reverse engineering pieces of software. So reverse engineering how it works, maybe there's maybe the software calls out to components out on the internet that are malicious. And you need to be able to pull those out. So all of these indicators are essentially pieces of evidence that we try and put together, and organizations want to alert on and stop, or at least investigate if it's happening in their organization. So our company provides a stream of this threat intelligence, and that product is incidentally called Threat Stream.
Okay. So it sounds analogous to maybe the kind of signatures that an antivirus type of company would produce. Is that a fair assessment, or maybe even another way of asking that, like what makes the stream streamy?
Mm-hmm. So different people can get this ground truth in different ways. So some of them are, in fact, antivirus companies. Some of them are organizations that do sort of a forensic investigation on incidents that happen after the fact. Some of them are, in fact, applying machine learning given their different data sets. So everyone has sort of a different strategy, both in their data collection and in how they validate it. Some of it is extremely qualitative by hiring cybersecurity experts. Some of it is extremely data-driven and quantitative, and pretty much everything you can imagine in between. And organizations really struggle from this problem of which one do I pick? And then if they can decide that, then they still have this issue of how reliable is that stream? So one of the things that in our platform we do, our machine learning use case, is to give people an assessment of how confident are we in this indicator from the stream. So we're able to, you buy sort of a big database of this is what all the badness is. You pay a particular provider. Then we run our own, largely regression-based, like ensemble regression, on the input feeds that they give us. And then we use that to sort of augment a lot of the incoming feeds, especially when we go out to the internet, collect free and open source data. Then we pull back data, and how reliable is this particular indicator? How reliable is this feed in general? So that's where we use a lot of our scoring algorithms to help separate, how seriously should you take an action on this particular indicator from this feed, because there's a drowning in data problem in cybersecurity.
Yes, I'd like to get more concrete on what the specific feeds are. I know some examples of things that I've seen folks doing are you could have, blacklisted IPs, for example, so that may be one. Is that an example of a feed in this case?
Sure. Yeah. So you could have, so we scrape a bunch of open source data. So that's part of it that we just sort of provide with the platform. And, intuitively it kind of makes sense that needs more vetting. And so the ML scoring is more important in that role, because if it's just an open source intelligence feed that comes down, having the scoring is particularly important. Whereas if you're paying for a particular feed, then you intuitively probably have a bit more confidence in it. So certainly you may be tipped off by honeypots, right? So honeypots are one example of how to collect this data. And that's basically we put a very vulnerable looking machine on the internet and just try and advertise that we're vulnerable and get people to attack us. So we have an open source project called the Modern HoneyNet, which is MHN, which is used to collect a lot of these, no matter what type of honeypot you have, then we can take this data and sort of centralize it, and it simplifies the data collection piece, no matter how many different types of honeypots you have. So that's an example of one of them.
So we've got the kind of the IP, the blacklisted IPs. Like, what are some other data sources that you're collecting, cleaning, providing that feed into, making, ultimately you're trying to make a determination whether, some activity is, likely to be a threat.
Yeah, absolutely. And so some organizations may choose to immediately block it. Other organizations may just want to monitor it and see what happened. Some organizations get breached and then need to do a retrospective evaluation of how did this get in? How did this happen? What was our hole? What was our chink in our armor? Yeah. And so with the retrospective evaluation, we've got another tool, Anomaly Enterprise, that's very focused on applying, basically taking the work off of your existing information aggregation tools, called a SIM, taking the workload off that and applying some ML, applying these known pieces of evidence like IPs and domains, and URLs and file hashes when they occur in the computer network.
Mm-hmm. Yeah, I'm still trying to wrap my head around, like, concretely the specific types of data that you'll ultimately be running machine learning algorithms over.
Right, sure. So there's two kind of main buckets. One is host-based data, and the other is network-based data. So on the host-based side, we have the most common is something like file hashes, right? So unique identifier of a file, because it's easy to rename a file. If it's a piece of malware, that's a really bad indicator. So we hash the contents of the file, or in more sophisticated cases, we hash subsets of the file to indicate maybe that there's a piece of the malware that's getting passed around, for example. So another kind of lower volume host-based piece of information that we track is things like function names and regexes, and so these types of sub pieces of a piece of software that could be used in a piece of malware, because it's when you start tracking by a file hash, so much of cybersecurity is an evolution, right? So we have an active adversary trying to elude us, which is part of what makes it a bit more of a unique space. And so one way this manifests is the type of data that we collect, for example, hashing files. When adversaries know that we do that to track their malware, they're going to try and find methods to get around it. So so one way to get around hashing of files is to just randomly add a little bit of gibberish in a non-executed portion of the file. And you can get into, in the ecosystem, like the economic ecosystem of malware, you can have automatic systems to just pad garbage in the end of the file, just to change the file hash, just to mislead you.
And is the idea with that to just render tools like yours not useful because there's so much noise out there, or are you trying to replicate the hash replicate the known good hash?
Well, the idea is that file hashes are a very commonly used strategy in cybersecurity in general. And so it's a very popular way to uniquely identify a file. And so adversaries, they're not doing it to elude us, they're doing it to elude everyone, right? And so then we get into, smaller parts of the file, right? So there's, in like a PE32, like an executable on Windows, you might have different sections. If you break down the assembly code, you might hash the import table for all the libraries that you import. So these more granular notions of hashing make it harder for the adversaries to avoid, but it requires a larger context of piecing together the different pieces to the puzzle.
So you've got the host-based data, you've got the network, NetFlow data, presumably, and perhaps other types of network data. That stuff is all coming off of ultimately routers, firewalls, network devices. And then you were talking about the difficulty of kind of coming to identifying ground truth. Like, you have all this data that you've collected. How do you go about labeling, or are you using unsupervised techniques, machine learning wise, to try to identify the bad actors?
So we're using most of our work is definitely in the supervised space. Okay. So like XGBoost, Random Forest, that sort of a space. Ensembles we see a lot of benefit from. What's interesting in the threat intelligence space, I've personally looked at a few different problems, and pretty reliably ensemble decision trees or ensemble regression trees end up being the best strategy.
So maybe can you talk a little bit about some of the different types of problems that you've looked at, and how do you go about defining the problems in a way that leads you to being able to solve them using ML?
Sure. So one of the important rules of machine learning, I think, is only use machine learning when you actually need it, right? Because most machine learning has false positives and false negatives. If you can come up with maybe logical expressions that don't have those, then you should use other methods, right? And so when I think of kind of the order of the tools that we use, if we can use the very first, most naive version of a tool is sort of a whitelist and blacklist. It's just big lists of exact matching. Then the next level of tool is a bit more of fuzzy matching, starting to get into the space of regexes and maybe signatures that are capturing patterns with a typical sort of programming language style of logical expressions, right? If we see these group of things possibly followed by another group of things. If those two methods fail, then your problem is really ripe for machine learning. And that's really the space we're interested in. And I feel like you need a little bit of intuition to believe that machine learning would work. So one example is domain generation algorithms. So for a long time, the strategy is when you have malware infecting your computer network and it calls out to maybe an IP or a domain, then you block that and you're good. Right. So first we did that with IPs, and then the bad guys became aware of it. So then they started calling out to domains. And then, once those were getting blocked and the strategy was successful, then the bad guys evolve yet again. And so the innovation after that was, in one sense, fast flux, which is sort of moving around IPs. But the one that really stuck is something called domain generation algorithms. So what that is in a piece of malware itself, you have a pseudo-random function that is known to the computer that's infected with the malware, and it's known to the adversary, maybe out on the internet, right? The guy that's running the whole botnet. So both of those 2 points know what the pseudo-random algorithm will predict for tomorrow. Yeah. And the problem is, in between those 2 points, no one knows. So the guys that are responsible to defend the network have no idea what the domains might be, tomorrow or the next day. And so this asymmetry that gets created between the infected malware and the bad guy on the internet know what's going to happen, and the good guys at the perimeter that have to stop it creates a pretty big disadvantage, right? Because there's no way they're going to know what domains need to be blocked. So the problem gets compounded. The asymmetry is compounded specifically because you not only have one domain, like per day, right? These domains would change every day, for example. But it's not just one. Maybe the malware calls out to 1,000 domains each day. And the bad guys only have to find one chink in your armor, and the good guys have to defend 100%. And so exploiting that asymmetry, the bad guys just maybe pick one or two of the domains that the malware will call out to tomorrow. They register that ahead of time, and that's how you utilize this communication mechanism. Because all malware, in order to be useful, needs to have some network connectivity, right? There's very few exceptions. And so, if you're stealing someone's credit card information, you need to send that back so it can be resold and you can monetize it, right? If you're doing economic espionage, you need to get the data out of the network and back into your organization. So this is a sort of fundamental rule of attacks, is that nearly every type of attack is about some sort of taking information. So then, since the bad guys are able to use this domain generation algorithm to get the information out of the network, then this is clearly a weak point in the defense of the good guys' perimeter, right? And so since it's a pseudo-random algorithm, the intuition is that humans can look at it and say, hey, that domain looks like it's gibberish, right? It might be XLJQBZF2, right?
Share those crazy looking domains.
Absolutely. And so it's usually the case that these very random sort of high entropy domains are affiliated with domain generation algorithms. There's a few exceptions, but the vast majority is like that. And so what's fascinating is that human analysts, when they see it, they're like, duh, I can pick that out really easy. Yeah. Why is this really a problem? Right. Well, because these algorithms may sort of tune down how aggressively they call out, start blending in with other traffic. And if you have to look through maybe hundreds of millions of domains that your organization has called out to yesterday, are you going to be able to look through all of them and pick this out? The answer is no. We need to automate. And you can't really automate this very well with logical expressions. And even if you did, you might be able to reconstruct maybe like a regex that describes this one particular algorithm. Oh, but by the way, there's different types of malware. They all use very different algorithms. They often have different seeds to their randomization. And so you really need an effective way to be able to distinguish between these random-looking domains and normal user traffic and activity. So this space is really what motivated my first project in the space of machine learning applied to cybersecurity. So we saw these things happening. This was in 2009, actually. Okay. So in 2009, I was talking to some colleagues, and we had realized this was a problem, that all these domains were happening out there in the internet. And so we put together a supervised prototype, and turned out it was able to detect them pretty effectively. Wow. So that was in about 2009. And then I think an interesting story that's kind of unique to security is that in a little over a year later, about a year and a half later, someone published a very, very similar strategy, a little less scalable, but a very similar strategy. So this was focused, I can give you the names, but it was from Texas AMU, and they published this paper, which was some good work, but we intentionally chose to not publish our strategy at the time, because there's this question of, if you tell an adversary you can detect them, what will happen? So the upside to the situation is we had been monitoring them. We had been monitoring the overall activity of these domain generation algorithm domains out on the internet. And so when the report was released at Usenix, it took about two to 3 weeks or so, and you can clearly see the points when the information from the conference got back to the adversaries. Wow. And we can see this, first it drops off nearly completely. And that happened, maybe lasted about 2 months or so. And then after that, you see a significant change in the variance of these. So it might have been something like, maybe like the weekend activity, was much higher, but the weekday was lower. Something like that. You see a big change in the variance of day-to-day activity than before the paper was released. I have a chart of this too.
All right. So you did this project. Tell us about how you went about solving the problem. What techniques did you use, and what did you learn in the process of deploying them?
Sure. So one thing that was very interesting was I thought was interesting was understanding which different models were more effective. And so I remember at the time I was using Weka APIs and instrumenting various type of algorithms. I was very interested in set up a cross-fold validation and figure out which algorithms are going to work better. The one that ultimately I found worked the best was a mix of AdaBoost with AdaBoost on Ripper. So if you've ever heard of the Ripper algorithm, it was made by William Cohen. It's a rule-based learner, very similar to a decision tree. But it's a non-boosted algorithm, and then boosting it after the fact ended up being more effective than something like maybe random forest out of the box.
Well, let's dig into all of this. So Weka, I've heard of a bunch of times. I don't know a whole lot about it. I get the impression that it has declined in popularity relative to newer things, but maybe what's your take on that? Tell me, what it is to you and the role that, where would you, what kind of situations would you turn to it?
I think the biggest sweet spot for Weka, in my opinion, is people who aren't real comfortable in programming. Okay. So it has a really good point-and-click GUI. And so it does have APIs. It certainly does. They're Java APIs, and it has a lot of algorithms implemented. So it's going to be much less than are implemented in R. But for being a machine learning framework, it's got a pretty good selection of APIs. It includes feature selection. It includes clustering. It includes a bit of neural nets. They've got a sort of repository for prototype code, which includes a lot of bioinformatics work. But I think, in my perspective, I think it's of all the tools I've seen, I think it's my favorite for someone who doesn't do programming. If you do programming, you can also use it. So there's a nice sort of stepping out, right? So you can go from just using it in a GUI to it's also got a command line where you can call, call a C45 classifier, for example, just from the command line with a CSV file. Okay. So it's got a nice sort of transition path to programming, and of course it's also got Java APIs as well. Mm-hmm. So I feel like the transition path from I don't program to I program a little bit, I think in Weka is really strong.
Okay, nice.
I think if you want to compare it to some, it's a little bit similar to Orange. So what I liked about Orange is that it has a canvas format. So you can have sort of a drag and drop GUI where you can assemble a pipeline, but Orange is primarily, Orange is Python based and Weka is Java based. With Orange, you can assemble sort of a pipeline of what operations you want to do with purely click and drop. You can also do this with RapidMiner. Okay.
And, all right. So that's, Weka. Then you mentioned AdaBoost. Tell us about that.
Yeah.
Actually, boosted decision trees in general. Let's, talk through kind of those and the role that they play in solving problems like this.
Yeah. So I think that, when you're getting introduced to machine learning, I think a very sort of helpful progression is to start with an ID3, which is a really basic decision tree, and then kind of move to a C45, which is a little bit more of a robust decision tree. And then to understand a bit more about ensembles, right? And so ensembles became a pretty hot topic around the early 2000s, something like that.
Well, maybe we should take a step back and talk about decision trees for folks that might not know about even a decision tree.
Sure. So, the general intuition with the decision tree is that we have a metric like information gain. So that might be when we say decision trees, we actually don't mean decision trees. They're actually decision tree induction algorithms. So they take the data, and from the data, they induce a decision tree. And that's what's a little bit confusing, because when you talk to maybe folks in the business side, you'll say a decision tree, and it's all about like action, and then there's an arrow for decisions, and then which way should we go. That is the end product of these decision tree algorithms. So the ability to induce those decision trees is really the key observation. So if you're really in the ML space and you say, oh, you know decision trees, right? It may mean a completely different thing than you think it means, right? So there's special ways these trees are constructed. I mean, I think a good conceptual understanding is take a metric like information gain, where we play around with drawing out a bunch of leaves in the tree, and then at the end of each leaf, we calculate how many, so it's maybe like if feature A is above 3, right, and that's one leaf, and if feature B is below 2, right, and if feature 3 is true. So we build out these levels of trees, and we assign information gain. The idea is if the likelihood is very high. So how many instances do we label correctly versus how many instances do we label correctly because of this branch? And when you have a high metric of usefulness with these, particularly with an individual branch, then it tends to sort of move up the tree.
So to make this more concrete, in the example we were discussing earlier, you may have, for example, feature A is IP on such and such blacklist. Feature B might be, is, hash on X file incorrect. And so you have some grouping of these features, and you're basically trying to create a tree that uses these features to determine whether the likelihood of a particular pattern is likely malicious. Right. And then the information gain metric is, as your decision tree induction algorithm is basically trying a bunch of permutations of these different features, and information gain is essentially asking the question, is this tree adding anything that, all the other ones that I've looked at, didn't tell me?
Yeah. So you draw out the tree. And then what's important, right? So much of data science is then about how do we control overfitting, right? And I feel like overfitting needs. I think it would be helpful in the field if people would spend some thought on more precise subgroups of overfitting, because I think there are subcategories of how things can be overfit, and it's not always necessarily such a binary observation. So tree pruning on the decision tree is usually one of the parameters that one would tune. And when you use tree pruning, the idea is you're trying to appreciate this trade-off between model fit versus model complexity, right? Since we have a data set that we're using to teach our model, then if we could build out our tree infinitely, well, we could memorize the data effectively. Right. And that's not what you want to do. It's important to generalize so you don't overfit. And so one of the important measurements to tweak with a decision tree is pruning. And so essentially what you're doing is adding a sort of a regularization or a penalty to when you grow out the tree too much. So you're trying to find the sweet spot between having a tree that can correctly classify everything according to the data that it saw versus having a really complex tree that might have just memorized all the data. Okay. And so that's a bit of an overview on decision trees. And then when we start talking about ADA boosting, we're talking about ensembles. And I think in the space of decision trees, Leo Breiman's work is really the seminal work here. He's the creator of random forests. And so I like to try and explain ensembles in a more general way. There's variations. So bagging and boosting and stacking are specific types of ensembles. But the general idea with ensembles is you have some sort of classifier. For example, it could be a decision tree, it could be an SVM. Some of the recent work is actually looking at ensembles of deep learning models. Right. And so the idea with an ensemble is that you construct multiple different trees. So in our decision tree case, you would construct a number of different estimators. And effectively, you're able to combine the knowledge from the different estimators. For example, one strategy is to use sort of a voting, right? And so every different estimator gets a vote toward the ultimate prediction. And so we talk about ensembles of these. And so you might use, dozens or hundreds or maybe even thousands, but usually like low hundreds is, or a few dozen is kind of a good starting place for how many ensembles to use. And it's almost always the case that when you combine these ensembles, you get better performance than you would with the decision tree alone.
And why is that?
It's because some of them, you can imagine sort of variations of some trees might overfit just a little bit, some might underfit just a little bit. And when you vote, I think it exploits more of a law of large numbers. And so you get more of an aggregate function, right? You see in society, you see these interesting things like in crowd voting, where maybe the intelligence, like wisdom of the crowds, right? The intelligence of the group is more valuable than the intelligence of any one individual. So I think that's some of the intuition of why ensembles are better.
And how are the different trees in the ensemble different? Are they different sets? Are they trained on different sets of features? Are they different hyperparameters? Are they, different? I know when I've seen ensembles, I've seen them in the case of different models. Like you might have a linear regression, that's good at figuring out one piece of your problem, and then some other type of model that's figuring out another subset of your problem, and then you kind of ensemble them together, or at least create a hierarchical model. When you're doing ensembles of decision trees, like what differentiates tree A from tree B?
Sure. And it of course depends on the parameters that are set, right? So it could be that you send different data to certain trees. It could be that you use different initialization parameters, right? And so, especially if you're creating your own algorithms, there's really no limit, and some of them you could use information gain as the metric of what is good, and in others you could use, like Gini entropy, for example.
What's that?
I don't think I really want to try and define Gini entropy. I've looked at a bunch of definitions, and I'm not to the point I can succinctly and clearly describe it. It's another metric like information gain that can be used to rate how good a model is, right? Or contributions to a model are. Yeah.
Okay. So AdaBoost, you've got a bunch of trees that you've created from sending them different subsets of your data, different initialization parameters. What does the AdaBoost algorithm do, and how's that different from? You were talking about actually boosting and bagging and all whatever. Kind of walk us through all that.
Yeah. So bagging, boosting, stacking. I think very, very practically, these are different ways to squeak a little bit of better performance out of your models. So you have these initial models that, you believe are pretty good. And I think it's one of the single most straightforward ways. How do I improve my accuracy without changing my data? Do ensembles, right? So try different parameters, try boosting, try bagging, try stacking. And you're nearly guaranteed to improve your performance, whether you're measuring, error rates or accuracy or MCC or anything, AUC.
Yeah, I know. I don't remember the exact stats, but some very large portion of recent Kaggle contest winners are all gradient boosted decision trees of one sort, ensembles of one sort or another.
Yeah, so XGBoost is really, I actually think Kaggle is one of the greatest practical sources to go to for learning about this stuff. I mean, we all need multiple tools, ensembles, if you will, ensembles of information that we can pull in, right? Podcasts like yours, and I think the Kaggle forums are a really valuable space. That's, a few years back, that's where, I got first exposed to XGBoost and how sort of it was able to add a gradient boosted component to our existing strategy of an ensemble decision tree. And in many cases, XGBoost performs better than random forest. But it involves a bit more tuning, right? So it involves basically all the tuning you would have in random forest. Maybe you've got something like half a dozen to a dozen parameters in random forest, but when you're tuning XGBoost, you're really looking at 1 to maybe 3 dozen different parameters to tune. And that can really take some time if you're doing sort of a grid search to try out a bunch of different levels. It's sort of a combinatorial problem, right? It's if you have 3 different settings for feature 1, 3 for 2, 3 for 3, then it's all multiplicative of how long it will take. And at the same time, you often want to do it with pretty large data sets because usually you'll get better performance if you're doing something like cross-fold validation. You'll probably get better performance out of it. So that can really take some time to compute.
Mm-hmm. So we were kind of walking through applying this stuff to the cybersecurity use case, and in that project you were describing, you ended up using decision trees to kind of get to basically to eke out your increased performance. How do you even think about performance in this context? Like what, I don't know if you can quote specific, like, error rates or something like that, or what are the key metrics, business metrics, I guess, and then how do those tie to, like metrics that you would be thinking about as a data scientist?
Well, actually, I can come back to describing that for how we score indicators and just pass along the confident indicators to our users. But I think there's an interesting story there when talking about the domain generation algorithm use case, because we have this situation of you have a few different families of malware. Let's say you have 3 families of malware, and they generate domain names, right? It's the domains that they'll call out to in the next day or 2 or whatever, right? And so intuitively, the first thought you would have is, okay, well, I'm going to measure, my performance metric. Maybe it's accuracy, maybe it's AUC or whatever. I'm going to measure that. I'm going to train on some of those domain names, but then I'm going to test on other domain names and, cross-fold validation, and that's very straightforward. Right. That's not the right metric to describe it. No matter whether you use AUC or accuracy or MCC or whatever metric you're using, that's simply the wrong problem you're measuring. Right. This is what I was meaning about kind of defining. I think there's value to us as a community to think about better definitions of overfitting. Okay. Because if I can predict new domains from the same malware that I've already looked at, what is the value? Even if it's 100% confidence or 100% accuracy, that's great, but I'm predicting different domains from the same malware families. What you want to be doing is predicting new domains from different malware families. And so when the research was coming out in the space, I was sort of surprised that all the metrics that was being done were always on detecting new domains from the same malware families, and people weren't measuring other malware families and the accuracy there. Does that point make sense? So it's maybe sort of that you need to look in a larger business case to observe what you should be measuring.
Mm-hmm. Yeah. So what you're saying is more like It's almost like a different approach to cross-validation. You're cross-validating across malware families instead of, just cross-validating within, one malware family.
Yeah. I think that's a great assessment of it, is to think about kind of the scope of the cross-validation and what you're ultimately trying to solve.
Any other interesting use cases or other projects that you guys are working on in the cybersecurity domain?
Well, I think one thing that's an interesting thing that we are tracking is that how well are adversaries sort of evolving to our methods, right? We could talk about this in the space of adversarial machine learning, right? The idea, I think, with adversarial machine learning is so in the cybersecurity domain, it's pretty common that good guys will first find strong signals of how to detect the bad guys. Eventually, the bad guys will know that the good guys are using that particular strong signal, and they'll try to avoid it. We see this case, this back and forth game happening. And so what machine learning allows us to do is potentially pick up on a lot of weak signals that we didn't quite realize were there, and then use those weak signals to detect the adversary. And that's kind of the state we're at now. There's a lot of cybersecurity companies trying to employ machine learning on obviously, weak signals to try and get good predictability to detect the bad guys, especially invariants, right? Invariant mechanisms that the bad guys aren't changing and moving around. Now, the concern is, are the bad guys using machine learning, right? Or will the bad guys use machine learning to try and blend in, right? The most straightforward way is, maybe they would try to model how we do it, for example. If the bad guys are modeling how the good guys do it, then constructing an outlier example isn't too hard. I mean, that's just the space of generative models. So if you can fit a generative model to approximate the algorithm the good guy is using, then this is a great way to sort of evade what the good guys are using. And that's one way that the space of generative adversarial networks, I think, is a little bit exciting, because most of the generative adversarial networks, the GANs, are used. So Ian Goodfellow was really a big pioneer in this space. And so he had some interesting observations and was able to put together a system where you have sort of a generator function as of a generative model, and then you have a discriminator function. The discriminator function is trying to detect when, in the case of maybe classifying images. So you have a generative function that's trying to generate an image, and the discriminative function is looking at the generative model. And then,
or the images that it produces.
Yeah,
right?
Exactly. It's looking at the images that the generative model produces, right? And then the discriminative function, its goal is to determine, was this determined by like a human or a computer, right? So most of this gets used because there's really impressive results. You end up seeing things like, you can use this in a few different ways. You can use it to like as a better mechanism to interpolate. So, for example, if you have a gap in an image and you want to fill in the image gap, you could use interpolation and try and sort of guess what it would be. The point is you've lost some information. And so when you try and algorithmically fill it in, it looks like it's algorithmically filled in.
Right. Meaning if you're averaging pixels or something like that, it just doesn't look right.
Exactly.
But in this case, you're training a generator, or you have a generator that's generating, this is a proposed way that I might fill this image in. And your discriminator is saying, that doesn't look good. That looks good. And so using the generative adversarial network approach tends to produce better looking infill than, your algorithmic approaches, your, averaging and stuff like that.
Yeah, that's a good assessment of it. And so a lot of times how it's used is just to try to produce something that's somewhat convincing. In the cybersecurity space, we can imagine how that could be used for a type of like poisoning and evasion. So if we want to generate maybe network data that looks believable, but also gets around your model, we can use the generator, and the discriminator together to optimally have the right sort of balance of these two components. And so in the long term, this is definitely a concern in the security space. As far as the maturity of the field, we're really just starting to get production machine learning to do a lot of the detection for network and malware and so forth. The past 2, 3, 4 years have been pretty hot in this space. And so we're really just maturing our process of machine learning deployed in cybersecurity. And so it's a little bit premature to talk about adversaries evading our model, but we definitely see the adversaries, when I was talking about strong signals and weak signals, we definitely see the adversaries keep picking up on the strong signals that the humans are finding and evolving. And so it's just the case that the way that the adversaries are evolving is suboptimal, because if they were using machine learning, they could learn more optimal strategies to avoid the good guys.
Interesting. So the good guys all hire these black hatters to try to, act like the bad guys and break them. Do the bad guys all hire white hatters to try to give them information about what the good guys might know about?
So far, as far as what we see adversaries doing to avoid good guys machine learning detection, for the ones we actually catch, right, because we're limited to just what we can catch, we haven't really seen deep model understanding coming from the bad guys. It's really still at that sort of subtle signal point. We do in a less ML type, in a less machine learning type of way, we do see bad guys, testing their malware code maybe by running it against a bunch of antivirus, right? Because that's just QA to the bad guys, right?
Right. So GANs, I've only ever seen that in the context of, images and deep neural nets. Have you seen GANs does GANs make sense in the context other than deep neural nets? That's what's interesting about it is, so Ian Goodfellow pretty much invented this space, and I think it was at NIPS this year. He gave a pretty famous tutorial on it, and in that he mentions you can plug in any supervised algorithm. Before there was GANs, there was work in adversarial machine learning. There were some folks at Berkeley that worked on it. There was folks at University of, how's it pronounced, Caligari. It's that island in the middle of the Mediterranean. Yeah, so I think it's the University of Caligari. They created a framework for just testing simple algorithms like SVMs and decision trees and these types of things. So they created a framework for testing those and creating sort of an adversarial space. So in my mind, those types of testing frameworks are examples of adversarial machine learning that are not GANs. Yeah, I wasn't aware of any of that stuff, so that's super interesting. And so in your context, are you applying GANs per se or non-neural network models to this? And are you applying neural nets elsewhere in the stuff you're doing?
So we are watching pretty closely as far as, do we need to start thinking of an adversarial component? And if we do, we'll certainly, the first indication we get, we're going to reorient our work. Because it could be a month out, it could be 10 years out, right? So at the moment, there's not enough data to convince me that it's really worth the big investment, but it's definitely worth kind of watching and keeping on the radar. Okay. As far as neural nets, they're less advantageous for us for the most part. I really tend to value interpretable models. And I think model interpretability in cybersecurity is uniquely important because so much of cybersecurity is about, do you have the right data? When you understand how your model works, it gives you insights into what current features are useful. You get a sense of how your model is working, which you don't really get with neural networks. And when you get that insight, then you can, if you've got some subject matter knowledge about how networks work and how operating systems work, you can start to have the conversation of, well, we should instrument at this level or collect this new type of data. So I think the biggest innovations in cybersecurity space are being able to interpret a model to go back to the data collection, make suggestions of new data to collect, and then improve the process and start all over there. Okay. Because we've kind of seen a pretty long history of, for the most part, having good data generally tends to be better than having really good algorithms. Of course, you want both, but if you have bad data, good algorithms don't do that much, right? And even deep neural nets usually require tremendous amounts of data. And so one of the nice things about our company is that when we're rating all these different feeds that come in order to help our end users, we can learn from all these different sources of labeled malicious data, which includes all sorts of different techniques for how do they detect malware, right? How much of it is an automated malware of maybe executing and watching the execution patterns versus statically analyzing a piece of code and reverse engineering and walking through it, or methods like setting up honeypots or other types of like network-based measurements, maybe monitoring the collection outside of a Tor node and just generally tracking this maliciousness. There's so many different ways to get insight into what malicious is. We do actually have a nice amount of data. So for that reason, I think deep neural nets might be on the horizon, but really understanding what data to use to judge the incoming streams of data is important. So model interpretability is huge for us.
Right. Yeah, that comes up in so many conversations I have with folks about as being a real challenge for employing neural nets right now, at least. Although, as that technique matures, there are some signs that will start to, that it's not necessarily, not necessarily antithetical to have interpretability with neural nets. It's just we're not there yet.
Absolutely. So, I think once we can cross that threshold of interpretability, I think it's going to be much more productive in the security space, at least for the companies that have enough data. Yeah.
Anything else you want to touch on before we wrap it up?
So how I got into machine learning was that in late 2008, I saw this, 60 Minutes news story. It was titled "Reading Your Mind." And it was some work happening at Carnegie Mellon with Tom Mitchell and Marcel Just. And they were some of the early folks to put people in fMRI images, fMRI brain imaging systems, and then use machine learning algorithms to uniquely identify various thought patterns. So the fMRI measures blood flow in your brain, so it's your data source. And then the ML algorithms were able to separate particular words and concepts. So they were able to show them a picture of a house or a hammer or something like that. And then fMRI brain image the blood flow in the brain, and then using the ML to predict what the person was thinking about. And so I saw that. It's a little creepy, but it's really cool. And I just got to thinking, wow, we should be using this for cybersecurity. And so that was a little bit earlier than a lot of the hot, exciting times when people started getting into. So I was a little early to the game in some extent. But I ended up a few years later publishing a paper with Tom Mitchell as well, and Alan Ritter who's now at Ohio State. And what we were doing is we had sort of a special. So we applied expectation regularization to detect patterns in Twitter streams. So there's this space of weak supervision in machine learning. And the idea is doing supervised learning when you have very few examples. And so it was mostly an NLP problem, and we were harvesting from data from the Twitterverse. And what we were trying to do was predict security, pull out the security events, so create sort of a security news source out of just the general Twitter stream. And so with just a few hand-labeled events, we were able to pull out, events on like DDoS and account hijacking. I think we labeled like a couple dozen events, and it had reasonably high accuracy given the weak supervision space, right, and very few labeled examples. So then we were able to sort of create these news streams of security events, right? So these are the events of people getting people's accounts getting hijacked today, and so able to track news stories. And I always thought that might be useful in security SOCs, right? To know security operation centers, to know what are the big events of the internet. Because in cybersecurity, you go into any fancy high-end cybersecurity operation center, and they've always got like CNN on the view screen. Right. Why? Because if 9/11 happens, it's really going to change the network characteristics, right? So you just need a basic exposure to the news. And so the thinking with some of this work was, if we can pull out the security news from the Twitterverse, then we can track some of these cyber events that are happening, the cyber news from Twitter. Right?
And the technique that you mentioned using was what?
Expectation regularization. So we're looking at the log likelihood. So we do a bunch of sort of n-gram analysis of looking at the tweet and the particular words that are involved. And we're able to take the log likelihood and then have a term for regularizing the label, so sort of a penalty for being wrong, right? And then also use L2 regularization as well. So two types of regularization as a penalty. The sort of basic idea is in the same way we don't want to grow our decision tree really large, we want to prune it back so we don't fit too tightly to the data. By having a lot of strong regularization, the intuition is so we'll try and pick up on the key patterns. And in this case, the key patterns were like nearby words in the tweet. And we used hashtags as well. And so from that, we were able to sort of create a security news service of sorts. Cool.
Does that still exist?
It existed about a year ago. I could try and email Alan and let you know if it gets back up. We had the security tweets domain and securitytweets.org, and that just pointed to like one of his test servers at Ohio State. Right now it's down, so I could ping him, ask if you could turn it back on.
Oh, it sounds like interesting work. Maybe we'll be able to include a link to the paper or something like that.
Yeah, so it was presented at the World Wide Web conference in 2015.
Okay.
Yeah.
Great. Well, Evan, thanks so much for meeting with me, for taking the time to join us here on the show. I think this may be the first time I've had a kind of a diehard TWiML listener on the show. So it's super exciting for me from that perspective. And I'm so glad you're able to join us here at the Strata event. Maybe before we go, what have you learned so far at the conference? Anything interesting?
Yeah, so there was two talks. This is pretty early in the conference, but two talks was sitting in. Some folks from Microsoft were talking about. They were talking about how they use machine learning in their security operations. In the Q&A section, we had a little bit of discussion of data imputation, because that's an area that's been on my radar lately. So in cybersecurity, we often have to make like a bunch of external API calls because that's part of our feature space. And so for whatever reason, if those API calls fail, then you're forced to impute that data. And can that imputed data then cause you to make significant errors? For example, if you were an adversary and you knew how to get me to impute my data, then I could misclassify because of that. So we ended up chatting about that a little bit in the Q&A section.
So valuable so far.
Yeah, absolutely. Absolutely. I love that there's a little bit of there's multiple sessions that are covering the cybersecurity use case now, because it used to just be basically media studies of video, audio, or images, or NLP, right? And so kind of the minority of us that are outside of those two areas, I don't think get quite as much attention in the machine learning space.
Awesome. Well, thanks again, and thanks for being on the show.
Great. Thanks for having me.
All right. Bye. All right, everyone. That's our show for today. Once again, thanks so much for listening and for your continued support. Don't forget to share your favorite quotes for one of our hot new TWiML stickers. You can share them via the show notes page, via Twitter, via our Facebook page, or via a comment on YouTube or SoundCloud. The notes for this week's show will be up on twimlai.com/talk/16, where you'll find links to Evan and the various resources mentioned in the show. Thanks so much for listening, and catch you next time.